We now begin to analyze rational functions, and you know the word rational refers to fractional, so we will have fractional equations, basically where we have to say that p of x and q of x have no factors in common, because we don't want to be able to factor and cancel this any further. In this first problem, we notice that the numerator factors into x plus 2 times x minus 2, and that this will cancel with the denominator there. The x plus 2's cancel out, and this rational function is basically equal to x minus 2. Now, you know how to graph x minus 2. It is a diagonal line having a y-intercept of -2 and a slope of 1. And it would be the graph of a line. However, if you go back to the original problem, you see that -2 is not part of the domain. And so at -2, we cannot have our graph, and we need to draw in an open circle there. And so basically, the graph of this function is that of a line with a hole removed. And there's a hole there at -2, -4. Now, we are starting with the exceptions to the rules. We have said that a rational function should not have factors in common, and most of the ones that we work with in this chapter won't. But we're showing you what would happen if that were the case. Now, this open hole here, an open circle, is known as a discontinuity. And there are three types of discontinuities. The removable type, which we've just seen, where you have one point removed from the graph. There's a non-removable, where you have a graph going up to an open circle, and then there's a gap there between another point, and there's no way you can just fill in the hole to make this a continuous curve. The third type of discontinuity is called an asymptotic or non-removable discontinuity, and it occurs when you have a graph such as y equals x that looks like this, and there's a vertical asymptote in the middle of your graph that's separating the two portions of your curve. We now want to analyze some notation, and every time you see these arrows, that's going to be the word approaches. And this is going to say as x approaches c from the right, or in this next case, from the left. Let's take a look at this next graph. We're asked to graph y equals 1 over x. Basically, 1 over 1 is equal to 1, 1 over 2 is equal to a half, and going in the other direction, 1 over a half is equal to 2. So you get this curve here, and you can never have 1 over 0, so there is a vertical asymptote at the y-axis. And it turns out that you have a horizontal asymptote along the x-axis. Now, let's use this graph and some of the notation from up above to describe this using what we call limit notation. I want to say as x approaches -infinity. In other words, as we go to the left, comma, f of x is going to approach the number 0. Is it ever going to equal 0? Is it ever going to touch that x-axis? No. But the function is going to approach that value. The y value, f of x, can be replaced with y, approaches 0. As x goes towards positive infinity to the right, well, now the graph is also approaching 0 from above, and so f of x is again approaching 0. Okay, that's the end behavior. Now let's look at the behavior in the center of our graph. As x approaches 0, little minus there stands for from the left. Now that is not to be confused with a negative number. That negative sign comes after the 0. As x approaches 0 from the left, as we get closer and closer and closer to the y-axis, what's happening to the y value? It's approaching -infinity. So f of x approaches -infinity. As x approaches 0 from the right, this is what's happening here. I'm getting closer and closer and closer to 0. What's happening to the y value? It's getting up higher and higher and higher. So this is going to say f of x approaches infinity. And this little plus sign right here is pronounced from the right.